Okay, hey, it's 13:25. We said we'd get started 13:25. Just a couple people here so far. Can I just get a hi from the people who are here, please? Hi, Mickeys. Good to see you. Could you guys, one of you guys, hey, hi, Micah. Well, I'm just going to post in case people aren't paying attention, which is possible. Hi, Luai. Okay, we just have a few people here so far. So I think, as I hope, people are still drifting in. Um, okay, well, everybody read my original message, so I'm assuming people will show up. Hi, Octave. So we got 5 of you here. Why don't we start by just briefly reviewing what we talked about, and especially what we did about the 2 labs previously. As people come in, please do say hi. Hi, Yanis and Sammy. Hi. Um, uh, we are piling in slowly here. So pop open. Okay, we are now at 8. 8. Okay, good. Let's get started. Close enough. Half of you are here. I hope more people are showing up, and obviously we will post the recording afterwards. Okay, so just a reminder where we come from. So yesterday I posted a couple videos showing how this Faraday's law can be used, at least qualitatively, to talk about how the current can be produced by changing the flux through a loop. We're going to take a little more of a detailed look at those concepts today. Specifically, we want to look at, first of all, flux. How do we find flux when it's not so simple? So up to now, we just said, okay, like we have basically a magnetic field, like that, okay? And we had a loop, simple enough. Here's a loop, right? And it had maybe a side length of a certain amount. I said, well, how do we find flux in that case? Pretty straightforward to do that, as long as the orientation is straightforward for your loop and the magnetic field is a constant value. But if the magnetic field is varying through space, and or the area is actually changing through time or whatever, it might be more complicated. So just wanted to help you figure this out. We talked about flux being equal to B dot A. And that, of course, implies something, namely that the area that you have actually has the same B everywhere. Otherwise, that doesn't make sense. Okay, so we can only talk about A dot B if B is actually the same everywhere. Otherwise, what's the point? Okay, so to be accommodating for that, if we do have a changing magnetic field, we would have to say actually, okay, well then B is a function of where we are, and that d phi, the amount of flux created by any little piece of area, would be the magnetic field at that point times the differential dA. So this is a vector product, which is it's a scalar product, a product of those two vectors, dot product. So it's a little scary, but it's a number because it's a dot product or a scalar product. So don't be too afraid. And then, of course, if we wanted to get the whole value for the flux, we then have to integrate that over that whole area. And that would be the total flux in that. Okay, so a couple things here. You could have this situation, for example, where we have maybe a side length A. It's a square, fine. But maybe the magnetic field is actually not constant. So B might be a magnetic field that varies as a function of X. Okay, what do I mean by that? I mean, let's imagine we have a coordinate system here. So let's say, for example, we put a coordinate system in like this, X, Y, okay? And let's say we're actually going to have a value of, at this location, which is of course A, okay? And let's say B of A is equal to B0, some value. And let's say it's linearly increasing from the beginning here where it's 0 up to the value where it is there. So we're going to actually erase these x's here because now we're going to say there's no magnetic field over here. And instead, the magnetic field starts here at the y-axis. So B of 0 is 0. Okay. And we're going to say that it increases, and we can symbolize that by saying, now this is not very technical, we're going to say big X is here, increasing, and then even bigger over here. So it's increasing linearly as we go to the right. Okay, just to do an example. So how would we take that information that we have here and express it? Okay, well, we'd say, okay, B of X would be equal to X divided by A times B0. Okay, so that would mean that if we plug in X equals 0, which was our first condition, B of 0 is 0. Then we plug in A for X, we would get A divided by A, which is 1. So B of X at position A would be B0. Okay, so fine. So we're saying here at this location, there, B is equal to B0. And here, B is equal to 0. And in between, it's linearly increasing. So we just defined it. Here's our function. And just to do an example, we can say, okay, let's figure that out. So we're going to look at our little square here and think, okay, well, we're going to move along in the x direction. To get this, we only need to think about integrating in the x direction from 0 to x. And for each position, because in the y direction it's constant, we can just take our position. So here's x, okay? At that position, this is our differential. The width of this is dx, okay? And we're going to kind of look at just this area right here. And that is dA of width dx and height a. Okay, so I'm just going to write here dA equals a times dx. The area that's showing up there. Oh, anybody else only get 480p? Okay, I don't even know what that means. So that's the resolution on that, I'm assuming, correct? Okay, I don't know. Oh man, this is kind of glary. I have this light here. That helping to have less glare? I think it is. Good. Ditto. It's very blurry. Okay, let me see if I go back and actually wave back here, whether it focuses in on that a little bit more. Not so much. Okay, what if I got a little, got a very professional system here. You guys would be amazed. I've got a table and a chair on top of it. Yay, technology is amazing. Okay, we're going to zoom in a little bit into that. Better? Okay, I can get a little closer. Let me scooch that even closer, and then I think we can get a little bit more. Wow, thank God they're providing us with all the equipment we need for this distance learning thing. Okay, so here we go. Better? Even closer? Okay, I've got the 3 more inches that I'm gonna fall off the table with this. I think I might be too close, but also I do wanna have a little bit of area to work in. Okay? How are we doing? That's good? Okay. Good. Okay, so just doing a quick, okay, so we have a square. This is a kind of a wire loop, okay? And we have a magnetic field that varies as long as you go along the x direction. So it increases, okay? And the value at position A would be B0, position value at A would be 0, and it linearly increases. But we're not gonna worry about it over there. And the height of this is the square, so the height is also A. And we're wanting to find the total flux, which would be the integral of the flux differential. And then your integral would be for the flux, the integral of B dA. Now we've chosen a little bit of an easier situation. It's a flat surface. We don't have it like bendy or some crazy crap like that, where then it would change its angle to B, which would be possible. Okay, so think now everything that's relevant you've got on your screen. Okay, so it ends down here, but there's nothing I wrote below that. Okay. Okay, so we'd like to find the flux, which means we need to integrate the differential for the flux, and of course it's B times dA. And like I said, it's not curving, so that's not a changing value for the angle changing, and we don't have to worry about that. That's good. We still got to do a little calculus. It's pretty straightforward calculus because we've got a b of x function which is changing, and our dx value here at position x is the width of this thing. At that point, dx times the area is the area differential. dA is a, the height, times the width dx for this rectangular strip of width dx. Okay, so we can use those 2 pieces of information, dA is this, and b of x is that, to then go into our integral. And we can go just here, good. So we have phi is equal to integral b dA, okay, integral, and now we're going to integrate b, that's x over a, times b0, which is a constant, okay, that is b. And then dA is a times dx, a times dx. Wrote that down, worked out okay. We do need the integration limits, meaning we need to make sure we're integrating the correct values of x. So x varies in this case from this starting point, which is on the y-axis, so x is 0, up to x equals a. So let's put those integration limits on here, 0 and a. There we go. And we should be okay now. Now we've got a few simplifications that we can do, not just a few, but just one exactly. So the A cancels out this A. So it's just x b0 dx. And the b0 can be pulled out. Okay, so we're going to go over here. We go b0 times the integral from 0 to a. Then we have x dx. Okay, that's a very straightforward integral, and we can just give us a little more space by kind of scrolling down here. So to get that integral, then we're going to say this is equal to b0 still up front. Then we do our integral sign. We're just integrating x, so that will be x squared over 2. And our integration limits are 0 to a. There we go. All right. Then we can plug in a, and we get a squared over 2. 0 plugging in gets 0. So we get b0 times a squared divided by 2 as our flux through this loop. Now that shouldn't be a surprise if you take a look at that expression, that would be our flux through there. I just did one example just to try it out to make sure you guys understand the process. But of course, b0 a squared would be the flux if b0 was the same all the way through the loop, and it was b0. But because it's varying from 0 to b0 here, on average, the magnetic field is b0 over 2. So b0 over 2 times a squared makes sense for the total flux. Okay, so that's just an example of how to use that equation to find the flux given a varying function for the magnetic field, which could be anything. They could have some crazy exponential increase or a sign increase or whatever, but the basic idea would be the same for finding that. Okay, that being said, let me actually come back and have you guys take a look at our equation sheet and kind of show you where we are, but I think that's useful at this point. So our equation sheet, let me see if this works. That is super awkward. All right, so the top law there, phi equals integral b dA. That's the one we're talking about. So you see the unit we're doing here, unit 5, just has those 4 equations. There's really not much there. So that's supposed to be encouraging. I hope that is encouraging. It's a smaller unit, 16% on the sheet, but we got that down. Now we're moving our way through part 1 on our layout of the curriculum for the course. And specifically, the top is cut off of the yes, I know. I'm going to come back in just a second. So if you take a look at what we're supposed to know, sorry, we're in electromagnetism. That's kind of the document we're looking at right now. Okay, so there we go. And the first part, part 1, we're almost done with. That is this side. The back page has 2 and 3, which are smaller topics, but we do want to make sure that we've got these things covered. Okay, thanks, Giannis. So here we go, and let's read it through just to make sure. So this part 1 of Unit E, electromagnetic induction, including Faraday's law and Lenz's law. Students should understand the concept of magnetic flux so they can, 1, calculate the flux of a uniform magnetic field through a loop of arbitrary orientation. So we didn't rotate, but we'll do that in a second just to try it out, but I think it's rather straightforward, more so than part 2, and that's the part we just covered, which is E1A2. Use integration to calculate the flux of a non-uniform magnetic field whose magnitude is a function of one coordinate through a rectangular loop perpendicular to the field. So we've got that covered. This is the flux through the shaded part of the loop. No, this is the total flux over the entire loop. The shaded part here is just d phi. So let me just back this up again a second, just turn it up here again to make this sure that you guys understood what we just did. So, okay, all right, we have a loop. It has a width of a from here to there and a height of a from there to there. In order to find the total flux for a varying magnetic field, or magnetic field varies, that means it's a function of position x. So initially it's 0, and over here it's b0. In order to find the total flux, we had to put this functional dependence for b in our equation for our integral d phi, which is the integral of b dot dA. And b dot dA, that's the differential amount of flux that we need to add up to get the whole flux through the loop. And this little segment here of width dx and height a has a certain amount of flux. And that flux depends on the area. The area of that little strip is the height, there, a times the width, dx, okay? That's the area. And then the flux, of course, would be the area, that differential area, times the magnetic field, okay? So if we insert that equation in there, that's right there. So that is B, and that, oh, colors will be good here. So, and then let's do this one. That's black. Did it fall down? So, and this is dA, right there, A dx. So the integral of B dot dA, where this is B and this is dA. Hi, Gio. So you can, if you want to, you can watch it later. This applies to anybody else if they have power failures or other problems. Okay. Even online, you're super late. Oh, Gio is. Yeah. Okay, good. So that's that. And we will do, I don't think we have to do an example of a, I'll take a picture of this and then I'll post it later onto, maybe I can just post it now. That would actually be a good idea. Let's do that. Then you can actually look at it in the group. And then also maybe. There. Okay, so I've posted the picture and then you can take a look at that. And I'll wipe this and then we're going to move on, okay? So let's take a look. We have 23 minutes, half periods right now. Wow, this is erasing great. Be nicer with a tablet probably that I can somehow link in to like a picture, or I'm an inset or something like that. Some of those pros on YouTube use, but I don't have the tech for that right now. So we're gonna have to deal with this. Okay, good. So if we have, okay, that works fine. Just close up. Good. Okay, so the second question was, what if we have an angle? So let's say we have a loop that is inside a magnetic field. So we're going to just take a top view of that loop. I'm going to say, okay, here's our loop, and it has a length of A, fine. And this is the top. And then the side view of this thing would be like more like this, right? A, good. But now we're just looking at the top of it, just to explain what we're looking at. And let's say we have a magnetic field that is flowing through there and goes this way. That's the magnetic field left to right. Okay, so let's take a look here in terms of figuring this out for how much magnetic field there is, magnetic flux there is through this loop. Now, we're kind of imagining, kind of just to kind of illustrate what this is, let's imagine this is something that is like rotating, that we have on an axle kind of like this, and we could rotate it because that's what we're looking at when we're looking at a generator is some kind of loop or loop assembly, a stack of coils, solenoid, rotating inside a magnetic field. Okay, so we're looking at this and saying, okay, well, what's going on here in terms of the magnetic flux? So reminder, this is a little bit confusing. A is a vector, okay, which is like, what? Okay, and just to illustrate what that means, the area is the magnitude of that vector. So that's a squared in this case, straightforward in this case, okay? But the other part, the direction, okay, direction is perpendicular to A. Now, what that means is that if we have this loop here, we're kind of imagining this loop sitting on top of this thing, like that's a loop like that, okay? Or it's a piece of paper. Maybe that's a better way of illustrating this. So we have this piece of paper sitting on top of this. That's so here's our loop of width A, and then this is a plane, okay? It's a plane, not a flying plane, but like a plane that's has a surface, and the perpendicular direction would be in that direction, okay? And if you move this thing around, that direction of A is always perpendicular to that surface, okay? And maybe it would be even helpful to kind of think about it like, kind of like a vector is like a pen poking out of that area. And that maybe illustrates for you what direction in each case A points. So we've got this thing set up here, and that means, of course, that A points in this direction. This is the vector A. Okay, now let's take a look at this. We've rotated this in a certain direction. What we need here is the angle between, whoopsie, between the vector A and that's a little awkward that I did it like that. I'm going to make that little red line here thicker. Make it just kind of go through there. Otherwise, it's hard to see the angle. Okay, there we go. Okay, that helpful? Hope that's helpful. Okay, and we have this kind of on one spot. Okay, so we have an angle here that the vector. Oh, okay, that's a good question. Yain. So geoset's the same thing. It's not really the same thing. The problem, so basically, what we're looking then is at the flux through the two sides, okay? And there are two sides to that loop, right? So here's the loop. There's this side and there's this side. And there's flux through here and there's flux through there. And one's the negative of the other, okay? So when you put in the arrow in this direction, your result will indicate to you what kind of flux is coming in this direction. And if you set up the other way, it's flux in the other direction. It will flip the sign. That's what I'm saying. So of course, flux from the left to the right, we call that positive, that's fine. Flux from the right to the left, we call that negative, that's fine. We could also orient the arrow the other direction. And all that does is effectively flip the sign. And one flux is then defined as positive and the other flux is defined as negative. The magnitude is not necessarily the key thing, but the change, the rate of change is what matters because we're going to be looking at if we want to find Faraday's law. Okay, so let's find that flux. In this case, is a pretty straightforward situation. We've got an angle between the two, that is theta. Call that theta, and just a reminder that the dot product, A dot B is equal to A times B times the cosine of theta, and that's it. Okay, so there you go, A, B, cosine theta, and that's all you're doing here, but just explain kind of what's going on here in terms of the situation. Okay, good. Now we can take this idea and actually move from here to Faraday's law. Okay, talking about Faraday's law yesterday, we introduced the idea that for this kind of wire loop or a stack of wire loops, which would be a solenoid, there really are, was it 3 ways? I think there were 3 ways we could vary the flux. So option 1 was changing the area that is in the magnetic field and thereby changing the flux. It was 1. And we did that by moving a loop in or out of a magnetic field. Okay? We could also do it by just taking a loop and making it a different shape. So for example, if you had a wire, right, you could have a wire that's like this, and you can say, okay, I'm going to take my 2 hands. You see that over there? Okay, and if we push the 2 loops together, that's a pretty good example. Let's do that. So let's say we have a magnetic field like that. That's magnetic field. And we're going to take that loop and kind of make it small. We've got it circular, and we squish it. Okay, we take that loop and we squish it and make it smaller. In that case, the area has become smaller, and therefore the flux into the board has also become smaller. Okay, so just as an example over here, how to do that. The B over. Anybody like, okay, well, let's figure out using Lenz's Lama ladder, if we compress this loop that way, what direction is the current flowing? Okay, reminder, we look at the phi external. Phi external is into the board. And because we're making the area smaller, the external flux through that loop is becoming smaller. So it's in minus. That in turn means that delta phi, the change of the external flux through that loop, is the opposite of in, which in that case would be out. Okay? In which case Lenz's law would say that because the external flux change is out, the internal, I'll maybe change colors, the flux that's induced, phi induced, has to be in, the opposite. That's Lenz's law. So this thing, the loop, is generating a magnetic flux that goes into the board. And if the magnetic flux generated by the loop is into the board, we can figure out the direction of the magnetic, the current causing that magnetic field. Magnetic flux is in, so the current needs to be clockwise. Okay, so this means I, and we're again using the right-hand rule here. Oopsie, sorry, no, right, that's applied, and this is clockwise. Okay, that's the induced current in the loop. Right, a little review of Lenz's Lama ladder. Okay, so that's happening. We can change the area of the loop to change the magnetic field, magnetic flux. We can change the magnetic field by oftentimes changing the current that is being applied to an external solenoid to generate this. Okay. We can also change the angle of the loop or stack of loops relative to the magnetic field. And that's kind of this idea where this is the flux. So if theta were a function of time, right? So for example, if theta was just straight up rotating, meaning theta is just increasing, decreasing, increasing, decreasing in a constant fashion, we could then find the flux change in that case, and from from Faraday's law, then find the induced current. Okay, good. So let's assume that theta is just a function of time. So we would say theta is equal to 2 pi times the frequency times t. Okay? Does that make sense? Theta equals 2 pi f times t for just a constant rotation process. Constant rotation at f. Let me just kind of make sure that makes sense. Okay, you guys still there? I think you're there. Okay, so we're going to look at this and say, what if this is rotating at a constant rate, meaning frequency of rotation for this thing is f. Okay, and then of course 2 pi f would be how far you've spun. So frequency is 1 hertz, for example. Then after 1 second be 2 pi. If f is 3 hertz, then 3 times per second we pass through 2 pi. Makes sense? Okay. Rhea says yes as well. Other people are being shy about this, and or yeah, being shy, or yeah, understand. Yes, yes. Okay, good. Okay, I'm going to take that as sufficient to feel like, okay, we're getting it. So what that means, this expression, 2 pi ft, or we've also expressed this previously as omega t, where omega is the angular frequency. So f is how many rotations per second, and omega is how many radians per second. So of course, omega is related to frequency by 2 pi f equal to omega, because there are 2 pi radians in a circle. Okay, so that's nice. And that means, of course, that we can take this expression for theta and actually place it into our equation right there for a simple rotation of the loop. Okay, so let's take a look what happens when we do that. We're going to take the area of the loop times b. I'm a little squeezed here, but that's okay. Cosine, gosh, this is barely squeezed. And then we're going to go omega t in here. Okay, and I'm limited in my space, so I'm trying to squeeze it in, and I'm going to make sure it's at least covering it there. So the flux, which is a times b, is ab cosine theta, which is a times b times cosine omega t. Okay, and I'm going to take a picture of this right now. I'm going to erase part of it, and we're getting towards the end, but at least we're introducing this idea. Okay. Okay. Okay, that works out. Yes. I need a power cord for my phone. Okay. Ben, you want it. Okay. All right. So let's take that. Let's see. We still got this thing rotating. I'd like to keep that part. I'm going to erase this. This seems pretty obvious. We're going to erase that down here. Okay. And we're going to erase that down here because we talked about that. And that was kind of a side example. We can erase that as well. There we go. And this is good stuff right here. And there we go. I'm going to kind of bring this up here. Maybe that's foolish of me, but let's just take that here. And we're also going to plug in the a squared. No, we're not going to leave. We're going to leave it like that. Okay. So we now have phi is equal to a times b times cosine omega t. Okay. Good. Good. So now we're looking at that being the flux, and the flux is changing, okay? The flux is changing, and of course that means that if that's the case, that means we will generate EMF. We examined changing flux due to angle change and area change, correct. So we looked at area change. Right now we're looking at flux change due to changing the angle. For example, by taking a loop and or a stack of loops, which would just be a solenoid, and spinning it inside a magnetic field. Okay, good. So this is the flux as it's changing, okay? And of course, epsilon would be equal to, this is minus d phi dt. Now I left a little space here on purpose, okay? And the reason for that being is that we're thinking about this as one loop spinning inside this magnetic field. But of course, if I had more than one loop, 2 loops, 3 loops, 4 loops, then those EMFs from each individual loop would add up together, not unlike a stack of batteries in a flashlight. You have one battery in a flashlight, 1.5, 2, 3. 3 batteries, 4.5. Big fat one is 4 times 1.5 is 6 volts. So that means we're going to need to put in here the number of loops in the solenoid that is spinning inside the magnetic field. Okay, so let's put that in. There's a big fat N. And now we have the expression more correctly for a generator. Okay, so we can look at phi here, and we can take that derivative, pretty straightforward. And we can say, okay, if we take the derivative, let's leave the minus sign in here, remembering the minus sign is really just a reminder that Lenz's law, N is the number of loops. So N is number of loops of the solenoid. Okay, big N. Little n, as you typed it, is the loop density, which we're not doing here. Okay, so the number of loops, 3, 200, 2000, whatever it is, spinning, minus n, the d phi dt. Let's take a look at what we have here. We have a b cosine omega t. So the a is a constant, the b is a constant, and then we need to take the derivative, and I'll just write it here, of cosine omega t. Is this coming in focus? I hope. Yes, the EMFs of the loops add together. They basically, and the way to think about it is, just like the batteries of the flashlight also stack up, or another possibility is some ski resorts are set up this way. You have one lift get you to a certain level, and then you get off the lift and you get on another lift, and that lift lifts you up to another level. So that's kind of a similar situation here, where the EMFs add together. Okay, just like a battery. Okay, minus NAB dt cosine omega t. The derivative of cosine is sine, no, minus sine, okay? And so minus sine, and then also you have omega popping out. So that means that we get equals minus NAB times minus omega, oopsie, sorry, sine omega t. So there we go. And then if we write that all out, the minus cancel, we get plus N A B times sine omega t. There we go. So that is the EMF we're generating here with a generator. So a generator, the amount of voltage it generates will depend on the magnetic field, the area of the loops or the solenoid, the number of loops in the solenoid, and also what matters here is omega that I lost. Hang on a second. Sorry. So N times A times B times omega. So just a reminder, yeah, that was my fault. Thank you, Hannah. Yes. So just a reminder that, yes, I got it. It's right there. We got it back. So that we yesterday saw the demonstration for that awesome experiment set up by Frau Rückeis. The loops spinning inside the two Helmholtz coils. As we increase the frequency, the voltage and therefore the current also increased, which is a great demonstration of exactly this concept of how AC current is generated. Okay, this is an AC voltage, and of course the current would also be an AC voltage. We're now at the end of our class, and I hope that helped you. We will talk about best ways to move forward in terms of what we should do next. Monday we would have a Doppelstunde on Monday. What would you guys like to do for that time? Would you like to have another chalk talk or marker talk? Would we like to go through some problems? Do we want to meet just one of the periods? Do you guys have any feedback right now, or do you want to give me feedback later? What do you guys want to do? Okay. The first votes come in as one of each, which is okay. We could split our time. A little more chalk talk. How much more material do we need to cover? So we are now in our sheet. This should bring us to the end, pretty much, of unit section 1, E1. Okay, and now we still have to go to inductance, which is a substantial subject, but that's okay, which is basically talking about how to formally integrate these kind of solenoids as inductors into circuits. We still have to do that, but we're making good progress. So let's definitely, why don't we do this? I'll offer both on Monday. Should we do both? Should we just use one of the periods? Okay, let's have a conversation. Chat talk on inductance sounds good. I suggest we continue with class time learning new things and find a time Wednesday to do problems. Okay, so I think we're going to delay problems and do chalk talk on Monday and or a whiteboard talk. So on Monday, we will, during regular class time, continue to learn material. Okay, we are on Monday going to, are we going to dare do 2 periods of this? 2 periods? Do we do it? You want to do it? Yes? Both periods? No. 2 is too many? Let's go. All right. Strange doesn't want to do it. It's going to Strange get outvoted. I think he is, but let's see what happens. I think 1 is enough. That we know what you think, Strangely enough. Okay, everybody else? There we go. 2 periods. 2 would be helpful. Okay, Monday we're going to do full Doppelstunde from 14:15 till 15:50, like we normally do. Okay, so Monday class, same time, same channel, and we have to meet during class time. That's been announced by the powers that be. So we have class regular time on Monday, 14:15 to 15:50. Okay, have a great weekend, guys. You should be able to do problems from section E1 at this point. So, or 5.1 is, I think, what it's called on the homework sets. So if you have some time over the weekend, yes, you'll get a 5-minute break to get your Streuselschnecke. That's absolutely true. And otherwise, hopefully you can get started on some problems, and I'll see you guys on Monday.